In a previous video, we found the Laplace transform of t and found it to be 1 over t squared. Let's verify something here. Right, the table of Laplace transform of t is 1 over, well, s squared, not t squared. Yeah, 1 over s squared. Alright, so the Laplace transform of t is 1 over s squared. Good. Now, we also multiplied the function by e to the at in a previous video and found a general Laplace transform of it. Now we're going to be specific. This is a specific example. We're using t instead of just f of t. So f of t is t. So we want to find the Laplace transform of e to the at times t. Alright, so let's go ahead. Here, this is equal to, so the Laplace transform of e to the at of t is equal to the integral from 0 to infinity of e to the at, or the definition of Laplace transform. The Laplace transform of a function is the integral from 0 to infinity of e to the negative st times the function e to the at of t. So the function is e to the at times t, and then dt, because t is our variable. So here, look at this. We could use our knowledge of indices to combine these, right? Now, this is equal to the integral from 0 to infinity of e to the, you add the indices, you have the same base e raised to the power of different indices, and they multiplied, you add the indices, so it's negative st plus at of t dt. Suppose we move the negative st to the right and the at to the left. Now this plus negative st, but we need the positive sign here anymore. So that's what we have there. We could factor out t. Alright, so let's factorize and put t outside the bracket. This t would go because we would have only one t. Alright, so we have this here. Now remember, the Laplace transform of a function, let's write it over here. The Laplace transform of f of t is equal to e to the negative st f of t. No, the integral from 0 to infinity of e to the negative st f of t dt. So we want it to be in the form e to the negative something, some function of t there, dt. So let's do that. If we rewrite this, we're going to have, this is equal to the integral from 0 to infinity of, we're going to have e to a negative. So let's multiply. If we multiply the t by negative 1 and multiply inside the bracket by negative 1, it's like we're multiplying this, all of this, by negative 1 times negative 1. So what we have is positive 1. Alright? Negative 1 by negative 1 is positive 1. So the value won't change. So t times negative 1 is negative t inside the bracket, if we multiply, the negative s will become, if we multiply by negative 1, the negative s will become positive s. Let's put it here. And the positive a will become negative a. So it's s minus a. You see that? Alright. Times t dt. Good. So we have this now. We have the integral of two functions of t multiplied. So let's use integration by parts. Remember what integration by parts formula say? The integral of u dv, right, is equal to u v minus the integral of v du. Good. Now we want to make one of these, either this or this, u. Which one do we make u? Well, we want to make the one that simplifies when we differentiate it. Because whatever we make u, we're going to have to move from u to the u. And we have to differentiate it. So, make u be equal to t. So that when we differentiate and get du, we get 1. Alright? We're differentiating with respect to t now. Just like how we differentiate x with respect to x, and we get 1. When we differentiate t with respect to t, we get 1. So, of course, dv would be e to the negative t s minus a. So that's e to the negative t s minus a. Alright? So that v then, when you differentiate v, well, when we integrate, because to go from dv to v, you have to integrate. You're going from the derivative of v to v itself. You have to integrate, right? So v is e to the negative t s minus a over s minus a. You use integration by substitution here, right? You have to remember your integration by substitution when you're dealing with something like this. So if you're confused about you get that over s minus a and you don't remember the integration by substitution, suppose you have, say, you have the integral of e to the negative t s minus a dt. Let u be equal to negative t s minus a. Then du by dt would be, when you differentiate this, just like how we differentiate x times a number, how we get the number, we differentiate t times the number, how we get back the number. So it's going to be s negative s minus a. Alright? So now, here, this is du by dt. This is dt. So dt would be equal to du, when you transpose du over negative s minus a. Right? And then, this is just reminding you of why this is not integration by substitution. So, we soon come back to this. So, what you have is the integral of e to the u dt. But dt is going to be du over negative s minus a. Right? So, oh, it's negative. I should have a negative. I didn't remember to put the negative. I just realized it. Good thing I went through this, so I realize that it should be over negative s minus a. Negative s minus a. So we put the negative s minus a outside of the integral sign. So it's negative s minus a integral of e to the u du. But you remember, just like how when you integrate e to the x dx, when you get back e to the x, when you integrate e to the u du, you get back e to the u. But u was what? U was negative t s minus a. So you just rewrite this as 1 over negative s minus a e to the negative t s minus a. So we have it over s minus a, right? So that's what happened. All right, so back to this now. Just in case you didn't remember, and it might throw off your concentration and flow of understanding. So back to this. This is where we reached. So here now, what we have is the integral of u dv equal uv minus integral of v du. So let's put in our uv minus integral of v du. So our u, which is t, our v, which is e to the negative t s minus a over negative s minus a minus the integral of, writing it too close, you know, writing these things too close, let's put them down, right, give them some space, minus the integral of v, which is e to the negative t s minus a over negative s minus a du, and du was 1, so times 1, and this integral has t as the variable, so it's dt. All right, so let's put in the boundaries now, because remember we're going from 0 to infinity. So this, the boundaries are from 0 to infinity, and the boundary of integration from 0 to infinity. So let's put them in. So this is equal to upper boundary. Let's substitute infinity for t. So you have infinity multiplied by e to the negative. Now t is infinity, right? It approaches infinity. S minus a times infinity is just infinity. So it's infinity over negative s minus a constant, all right? Minus 0 now. T is 0. E to the t would be 0. Negative t, you're saying negative 0, but it's 0. 0 times s minus a is 0, whatever s minus a is. So it's e to the 0 over negative s minus a. See that? Now, e to the negative infinity is the same as 1 over e to the positive infinity. E to the infinity is infinity. So now it approaches infinity. 1 over infinity. 1 over an infinitely large number is 0. So this up top here becomes 0. Infinity times 0. If you choose a value for s, so that you can choose a value for s, you know. Imagine you choose a value for s, so that you have the integral approach 0 faster than it approaches infinity. So 0, this would become 0. So this goes 0 times e to the 0. E to the 0 is 1, and 0 times that is 0. 0 over negative s minus a is 0. All right. So all of that will approach 0. Minus. Now, even though I say t becomes infinity. Now remember, there is no specific number called infinity, right? It's imaginary. But you can have a value approaching infinity, but you never reach infinity, right? Now here, you see this one now? You see the negative s minus a is a constant. So we can take it outside of the integral sign. So you have minus 1 over negative s minus a. So the integral from 0 to infinity of e to the negative t s minus a dt. See that? Now, negative is a positive. So it becomes 1 over s minus a. The integral from 0 to infinity of e to the negative t s minus a dt. Alright, so let's carry out this integration and see what happens. This is equal to 1 over s minus a times this integral will become e to the negative t s minus a over negative s minus a. Alright? We're going from 0 to infinity. Now, what will happen here? We've run out of scrolling space. So let's use this space over here to continue our work. Can't scroll down anymore. So let's come back up here. 1 over s minus a. So we have 1 over s minus a times what now? E to the negative t s minus a. So we have e to the negative t s minus a over, we're just rewriting this, negative s minus a from 0 to infinity. And it's negative s minus a. Are we going from 0 to infinity? Now, let's see what happens. This is 1 over s minus a. Now, upper boundary. We substitute the upper boundary. This is e to the negative t s minus a. But this is over negative s minus a. But t becomes infinity. S minus a times infinity is just infinity. Remember, there's no specific number known as infinity. We're just becoming infinitely large, right? Number approaches an infinitely large value. This infinity. E to the negative infinity is 1 over e to the positive infinity. But e to the positive infinity become an infinitely large number. So this becomes 1 over infinity. But 1 over an infinitely large number is 0. So this becomes 0. Alright? Alright, minus. We put in the lower boundary, which is 0. E to the negative t s minus a over negative s minus a. We're putting in 0 now for t. T is 0. This is 0. 0 times s minus a is 0. So the s minus a goes. When you say negative 0, it doesn't make sense. It's e to the 0. What is e to the 0? E to the 0 is 1. So, now, what you have here is 1 over s minus a times, this is 0. 0 minus negative 1 over s minus a. Now, here, minus negative 1 is positive 1. So we have 1 over s minus a s minus a. That's what we have. So 1 over s minus a s minus a is what we have. So here we can say that the integral of e to the at t is 1 over s minus a, which is s minus a squared. Alright. Is it correct? Let's verify it with our table of integrals. Or do we have it there? We have t, when you integrate it, you get 1 over s squared. Oh, we wouldn't have that. We wouldn't have that in our table of integral. But we have it here. Now, notice we have the Laplace transform of t become 1 over s squared. But the Laplace transform of e to the at times t become 1 over s minus a squared. So s is replaced by s minus a. Now, there's a certain name for this. This is a result from what you call the first shift theorem. Alright? The first shift theorem. So here, what we have is that the Laplace transform of a function of t equal some function of s. But the Laplace transform of e to the at times a function of t becomes a function of s minus a. So that is one example of what comes from the first shift theorem.